Hello everybody, this is our video solution to problem 15 from the Fall 2020 Math 210 final exam. Here we are trying to represent functions as power series. And we're told for at least one of them we have to define the radius of convergence, and no need to talk about the interval of convergence, it seems. And these look very, very similar. They both have this 5x in the numerator and some sort of 1 plus x squared in the denominator, but man, do order of operations matter. So here we're adding x squared to 1, and here we're adding x to 1 and then squaring the result, right? We're taking the square of x plus 1. So they're not the same function. And we're going to have to treat them actually very differently when we go to actually compute the power series expansions. So the first one is the easier of the two because, well, our primary power series expansion that we know, right, is the geometric series expansion. So if I look at x to the n at least 0, I know that this is equal to 1 over 1 minus x, at least provided that the absolute value of x is less than 1. Okay, radius of convergence here is 1. So this is what everything builds off of, okay, is our geometric series. So if I wanted to have 1 plus x squared, I would just take this x and replace it by negative x squared. Okay, so 1 over 1 plus x squared is equal to 1 over 1 minus negative x squared. And now I can put this into the geometric series formula. I get the series starting at 0 of, well, instead of x, negative x squared to the nth power. All right, I don't really want to leave it like this. All right, it's not really in the form of a power series. So I'm going to pull this negative out as an alternator. And then x squared to the n just becomes x to the 2n. All right, so there's a power series expansion. And in order for this convergence to happen, I knew that whatever I put inside, right, as my geometric series ratio has to have absolute value less than 1. So I would need that the absolute value of negative x squared is less than 1. But, okay, first, the absolute value is not going to worry about that negative. So this is the same as the absolute value of x squared. But that square can come out. And now I know that a quantity squared is less than 1, positive quantity squared is less than 1, if and only if that positive quantity itself is less than 1. And therefore, my radius of convergence is actually still going to be 1 in this case. All right, so am I done? Well, not quite. I'm almost done, but you see I got this 5x I have to deal with. But that's pretty easy to deal with, right? I just multiply this expression 1 over 1 plus x squared by 5x, which is simply going to include an extra 5 into this expression and one more power of x. So this is going to be the series starting at 0, alternator times 5 times x to the 2n plus 1, with radius of convergence still equal to 1. Okay, so that's the easy one. What do we do with the second one? Well, there's two, I think, very obvious approaches. One is a pretty good approach and one is not. So the obvious approach that I don't think is so great is to break this up. Okay, again, we can multiply the 5x in at the end, so ignore that for now. But imagine you had 1 over 1 plus x quantity squared, and you broke it up as 1 over 1 plus x times 1 over 1 plus x. So we could write down a series expansion for each of these. It's the same series expansion, and we get it in the same way as we did over here, only instead of a square, you wouldn't have a square, right? It should be minus x to the n. The downside of doing this, right? So we could do this and we get, okay, n at least 0, minus 1. In fact, let me use m here because that's actually going to be important. So I could write down this series expansion for 1 over 1 plus x, and then another copy of it. And just, I really want to be careful and not use the same index. Because what I would then have to do is multiply these two together, which we can do, but it's just annoying. What a pain. So I don't really want to do that, right? So instead, what I want to do is recognize that 1 over 1 plus x quantity squared is equal to 1 plus x to the negative 2 power. And I can get this as the derivative of something. What's the derivative of? Well, what if I took the derivative of 1 plus x to the negative 1? A negative would come out, and then I'd have 1 plus x to the negative 2. Hey, that's almost exactly what I have here. I just need to toss a negative in here. Okay, and this bit, okay, so this is negative the derivative of 1 over 1 plus x. Hey, that's exactly the thing we know how to compute a series expansion for. And if I go to take the derivative, I can just take the derivative term by term. And that's way easier than multiplying this out. Okay, so I can rewrite this as negative the derivative of this series starting at 0, an alternator, and then x to the n. And now I'm going to bring this derivative inside. In fact, I get to bring it all the way inside even the alternator. And so all I have to do is differentiate x to the n. So I get negative this sum, negative 1 to the n, nx to the n minus 1. All right. I actually am going to be able to start this now a little bit later, right? When n is equal to 0, well, this term is going to die. So I might as well even start this at 1. All right, fine. This negative can come inside and flip the sign of this alternator. So I end up with sum starting at 1, negative 1 to the n plus 1 times n times x to the n minus 1. It's nice when you write down a power series that you can write an x to the n if you can. I mean, when we had it before with an x to the 2n, it really wasn't worth messing around with that. But if we can just shift this, that always makes me feel better, particularly later on if we want to use this as part of, say, solving an ODE using power series. So I'm just going to do that. So I'm going to raise my n's by 1. Now, when I do that, this becomes an n plus 2, which is no different than just an n here with an alternator. This becomes an n plus 1. There's an x to the n. And you remember, if I increase my n inside of a sum, I have to decrease the index. So now my index can start at 0 again. Okay, so let's go back up. And we can now write this as, well, remember, there is this 5x we have to deal with. Fine. So we can start with 0, and we would have minus 1 to the n times n plus 1, x to the n. Oh, and we got to put the 5x. Okay, so let's see. We're going to sneak a 5 in. Then this becomes an n plus 1. And, oh my goodness, maybe I shouldn't have re-indexed before, huh? Yeah, so, okay, let me just slide this stuff down a little bit. So I can re-index to make that an n again. So when I re-index, the n goes down by 1. All right, well, with this, you can go down by 1, up by 1. I don't care. Then we have a 5. Okay, cool. N plus 1 turns back into an n. And then we get x to the n. And because we went down by 1, our index now goes back up by 1. How funny. All right, so we might have saved ourselves a little time by not re-indexing in the middle. We forgot about this 5x here. Okay, now what about the radius of convergence? Well, the original geometric series has radius of convergence 1. And when we do this 1 over 1 plus x, the only difference is that we need that the absolute value of negative x is less than 1. Well, that doesn't change, okay? So that's equivalent to saying the absolute value of x is less than 1. The radius of convergence is still 1. Well, what happens when we take the derivative? Well, we have a theorem which says, right, when differentiating a power series term by term, the radius of convergence does not change. The interval of convergence can. You might lose an endpoint or two, right? But you're not going to change the radius of convergence. So we conclude that the radius of convergence in this case is actually still equal to 1, right? Or, well, we can put it here too. Okay, so there is our power series expansion.